Okay, we are starting day 3 of our Unit 9 on probability. This is the multiplication rule. We also call this AND problem. So this little U-like shaped thing, upside down U, would be the probability of A and B happening. So the probability you're going to do this event and the next event, you take the probability of A times the probability of B. So a person chosen at random has a probability of 0.23 or 23% of being an only child. What's the probability that 4 random people are only children? You would take 0.23 times 0.23 times 0.23 times 0.23 because we have 4 random people, so we have 1, 2, 3, 4 times that probability. Because the probability that the first person is the only child does not affect the probability that the second person is an only child. And today we're going to round to 4 decimal places. So that would be 0.0028. And the reason we chose 4 is because a lot of these are very, very small percentage of chances. So if we round it to 2 decimal places, almost all our answers are going to come out to 0.00. So we're going to round to 4 decimal places today. Example 2, a person is chosen at random has a probability of 0.23 of being an only child. What is the probability that the 4 random people have siblings? So this is kind of like the opposite of this. If 0.23 is an only child, you take 1 minus 0.23. That means 0.77, or 77% of people have siblings, and only 23% of people are only children. So we still want 4 people. And only this time, all 4 of those are going to have the probability of 0.77 because they all have siblings. We're going to multiply all those numbers together, or 0.77, probability to the 4th power, because we want 4 of those, comes out to 0.3515. Alright, so kind of similar to what we just did, I would say we could pause the video and try these. Sue has a probability of 0.24 being bilingual. Stan has a probability of 0.39 of being bilingual. What's the probability that Sue and Stan are both bilingual? And notice this one has the word and. So and means we're going to multiply these probabilities together. So Sue would be 0.24 times 0.39 for Stan. And you get 0.0936, that they are both bilingual. The next one says Sue is bilingual, so we know that as 0.24, times says Stan is not bilingual. So if you take 1 minus 0.39, you're going to get 0.61. So we're going to do 0.24 times 0.61 to figure out what this probability is. 0.1464. Make that a little bigger. Probability that Stan is bilingual. Stan was 0.39 times, this says Sue is not bilingual. So if we take 1 minus 0.24, you get 0.76. So 0.39 for Stan times 0.76 for Sue not being bilingual. Multiply, you get 0.2964. This time neither Sue or Stan are bilingual, so we're doing the not versions of this. Sue not being bilingual is 0.76, and then Stan not being bilingual would be 0.61, and multiply, you get 0.4636. So these AND problems are when you multiply. A lot of probability problems that you're going to see on the ACT or in math classes revolve around a deck of cards. If you're not familiar with a deck of cards, there's 52 cards in a deck. There are 4 suits. How many suits are in a deck? There are 4, which means each suit has 13 cards. each. And to name them, we could say there's hearts, diamonds, spades, and clubs. Those are your 4 suits. We have hearts and diamonds are red. And we have spades and clubs are black. Boxes above that just represent, okay, what are cards? There's 13 cards, I have 13 boxes, so I said ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2. Each suit in a deck of cards has those 13 cards. So, we have Joe here. He's going to draw from a deck of cards. He's going to replace the card before he draws a second card. Whereas you have Jane here, she's going to draw from a deck of cards, but she doesn't replace. So we'll say without replacing. So we are drawing 2 cards here. The first card is an ace. So there are 4 out of 52. There are 4 aces in a deck. Times, if you replace that card, there are still 4 aces out of 52 probability in the deck. If you multiply these 2 fractions together, we're going to say that comes out to 0.0059. Let's think about the same situation with Jane. Jane pulls out an ace, that's 4 out of 52. If you want to pull out another ace, there's only 3 aces left out of 51 cards. So we took an ace out, so we have 1 less ace, and we also have 1 less card in the deck. 0.0045. This time, Joe is going to pull out an ace of spades. There's only 1 ace of spades in the deck. And he also wants to pull out a spade, but he puts that ace back, so there are 13 spades out of 52. So that gives us 0.0048. On this one, you can still pull out 1 ace of spades, but if you pull out that ace of spades, there's 1 less spade in the deck to pull out. So instead of 13 out of 52, we're going to say 12 out of 51. Because we took a spade out and a card. Queen and king, there are 4 queens times 4 kings equals 0.0059. Jane, though, pulls out the queen, 4 out of 52, times, she pulls out a queen, but she wants to pull out a king next. So technically, there's still 4 kings left, but now we only have 51 cards in the deck. So I put 0.006. If I round it correctly, it'd be 0.0060. Okay, now we're going to go back again. Kings, there are 4 out of 52. Cards are king. Times, and then I want to get a face card. So you have to think, a face card up here are your king, queen, and jack. Those are considered your face cards. They have faces on the cards. So there are 3 of those, but we have 4 suits. So 3 times 4 means there are 12 total face cards in a deck of cards. Again, we're multiplying these and writing down our decimal. So this time, I want to pull out a king. There are 4 kings out of 52. But if you pull out a king, that's considered a face card. So there's only 11 face cards left out of the 51 cards. So we took it down because the king is a face card. And I have 0.0166. Last one, this is, all of these we're drawing two cards, a king and a queen, a face card and a king, a spade or whatever. The last one we're drawing 4 cards this time, and I want the probability that all of them are 7. So Joe here, he's a real nice guy, he puts them all back. So 4 out of 52 times 4 out of 52. And you just do that 4 times, because if all the cards are in the deck, you have the same probability with each drawing to get a 7. So this one I rounded to more decimal places because it's so small. It comes out to 1, 2, 3, 4 zeros, and then a 4. And it might be like 3, 6, or 3, 5, but we rounded it up to 4. With Jane, though, she takes out a 7, so there's 4 out of 52 cards that are 7s. This time, if she takes out a 7, there's only 3 left out of 51. She takes out another one, there's only 2 left out of 50. Times there would be only 1 left out of 49. So Jane does not replace her card without replacing, so it goes down every time she takes one out. This one is it has 5 zeros. 1, 2, 3, 4, 5, and then a 4. Alright, let's look at the next side. And the next side is called mutually exclusive. A mutually exclusive event is an event with no common outcomes. Meaning there's no overlap between the two events. For instance, having blue eyes and brown hair. It's possible. It is possible. So if it is possible, it is not mutually exclusive. Okay? If it's not possible, then it's mutually exclusive. The two things cannot exist at the same time. So being over 6 foot tall and being 5'5", those two things cannot happen at the same time. So this is called mutually exclusive. Can't be over 6 foot and be 5 foot. The two can't happen at the same time. Let's see, having a permanent address in Kansas City and having a permanent address in St. Louis, Missouri. This is not possible. You can't live at both places permanently. So if you can't do both of those, then that is mutually exclusive. Taking geometry first black gold and weights on first black gold. So both of these classes are on first black gold. Can you take both of them? The answer would be no. This is mutually exclusive. Alright, now we're going to shift from doing and problems to this little thing is the intersection. This is or. A or B. So we're only going to pull out one card, and we want to figure out the probability that that one card is what we're looking for. So you take the probability of A plus the probability of B minus the probability of A and B. A situation like that would be they have something in common. So both A and B. So number 6 here, the probability of Stephanie being on time at school is 0.78. The probability that Stephanie is remembering her lunch is 0.84. The probability that Stephanie is being on time and remembering her lunch is 0.66. So that and comes from the multiplying of the 78 and the 84 is how they got the 66. So, probability that Stephanie is either on time or remembers her lunch. So we're going to say on time. That probability was 0.78 plus, I'm just going to put lunch here. She remembers her lunch was 0.84 minus both. When do both of those things happen? If you want when both of those things happen, you're going to take, in this case it's just 0.66. But if you didn't have that already worked out, I could take 0.78 times 0.84, and that comes out to 0.66. Instead, we are going to add these two together and subtract that one. This is kind of like the backwards version, the not version of something. What's the probability Stephanie will be late? She's on time 78%. She would be late 22%. So 0.22 for being late plus forgets her lunch. So 0.84 minus 1 minus 0.84 is 0.16. Okay, and then we have our equal sign, or then we have our minus sign. We're going to take 0.22 times 0.16. That's how many times does, what's the probability of her being late and forgetting her lunch? So you can enter all that in your calculator. And we get the answer is 0.3448. Alright, probability of owning a car at 16 is 0.34. The probability of having a job at 16 is 0.47. If Matt's 16, what's the probability he owns a car or has a job? So or is our adding and subtracting. So we know that it's possible for him to get a job. We're going to say he owns a car and a job. So owns a car is 0.34 plus has a job is 47% minus both. So we don't know how many times that he didn't have a job or a car. So or does own both of those. You're going to subtract 0.34 times 0.47. So both ones, when you have both situations, you want to multiply. We got 0.6502. Alright, wrapping this up now, cards are sometimes easier for some people and harder for others. Joe randomly draws a card from the standard deck. Find the probability of each. So these are all OR problems. OR problems are adding, and if there's overlap, you subtract it out. He's only drawn one card, so it doesn't matter if he replaces it or doesn't. We're only looking for one. So probability of an ace, there are 4 aces out of 52, plus the probability of a heart, there are 13 hearts. So I'll write the word ace, this is a heart, and then you subtract both ace and heart. So there is one ace that is a heart. Okay. You can get decimals or fractions here. If I wanted a fraction, that would be 17 minus 1 gives me 16 over 52, but we wrote them as decimals. I have 0.3077. So if you want to pause the video, check your work, try it, then just look at the notes that are worked out on Canvas. That would work too. So probability of a 5, there are 4 5s out of 52, probability of 10 is 4 5s, 4 10s out of 52. Minus the overlap. Well, there are 0 that are both a 5 and a 10. So 8 out of 52 equals 0.1538. Okay, probability of a face card, we decided every suit has 3, so that's 12 face cards out of 52. A spade, there are how many spades? 13 cards out of 52. Minus, do we have any face cards that are spades? So there are 3 face cards that are spades. So adding and subtracting, we come out to 0.4231. Last one, this was a typo. This should not say kind, it should say a king. So probability of a king is 4 out of 52. Probability of a queen is 4 out of 52. So that would be 8 out of 52. And that comes out 0.1538. So that wraps up everything. If you see an OR problem, we are adding and subtracting if there's anything that's overlapped. With an AND problem, we are multiplying.